Welcome. There's been a few questions which concern the overview of the practice activity, so I thought I would go over it in this video, apart from having gone over it in the lecture as well quite quickly. All right, so here we have this S-shaped rod. You can see that there is basically three components to it. There's one which you can see the mouse that I've placed over it. I call that the body A. I call this the body B, and I call this the body C. And together A, B, and C make this entire system, which we call S. So I think we are familiar with how a big system can be made up of many smaller systems. And so you can see that I'm calling each one of these pipes a subsystem of the grander system. So this is A, the vertical one is B, and then the one along X is C. Now, the question over here asks you to determine all the 9 elements, computing the moments of inertia and products of inertia, which give you the inertia matrix I within square brackets of the entire system about this point O. Okay, and so you can see that because this is a system of 3 bodies, I would have to first actually break it down into finding the inertia of A about O, inertia of B about O, and then inertia of C about O, right? So if you work backwards from the solution, what you see is I print the inertia matrix of S about O, but you can see that I compute it by saying, okay, this is going to be given by the inertia matrix of A about O. Then it's added to the inertia matrix of B about O and the inertia matrix of C about O. Where did I get this from? If you go to the theorems of computing moments of inertia, which was right above the practice activity in terms of the table of contents. If you click on that, you see that I have a system made up of 4 subsystems, so you can add up the individual products or moments of inertia, and the same is true for the entire inertia matrix as well as a result. So you can essentially just add up the inertia matrices as well, right? That's step 1. So then we need to have a way of computing the inertias or the inertia matrix for an individual system, right? Because you can see that the system has an inertia matrix about O that's given by the sum of 3 inertia matrices of each of those bodies, right? Like of A about this point O, of B about the point O, and of C about the point O. So I have to calculate each of these. Okay, now I'm not going to go over each and every one of these matrices, but I'll go over the first one and explain to you what's happening, right? So thinking about how we compute the moment of inertia of this pipe with respect to the point O, we have another theorem actually right above the composite theorem, which we call the parallel axis theorem. Now this one allows us to compute the moment of inertia of this body R with respect to an external point O. And at the very bottom, we've already given you the result. We've said that for this single rigid body R, if you want to compute its inertia matrix about the point O, it's broken down into computing the moment of inertia, so the inertia matrix about the mass center, and adding to that the inertia matrix of the mass center about the point O, right? So what we're saying is if I want this body's moment of inertia or product of inertia to be calculated with respect to a point O, I can do so by just computing its central moment of inertia, that is its moment of inertia about its mass center. And then to that we add the moment of inertia of this point with respect to that point, because this is a point mass, don't forget. So essentially what that means is if R is a pipe, then we've given you a table of what it looks like for a pipe, which is also called a slender rod, right? Like if you have an axis in the y direction, you're told that it's 1/12 ml squared. And if it's in the length direction, then we also tell you that it is 0. So we've told you over here that the product of inertia about the length of a pipe G is 0, and the moment of inertia is also 0. Okay, it's in all directions that it's 0 for the products of inertia, and the moment of inertia is just along the length, right? So that means that if there's a y here, and let's say there's an x going upwards, those two moments of inertia would be 1/12 ml squared, where m is the mass of the pipe and l is the length of the pipe, right? You can see all of that information is here. Now, there is no substitute for you actually solving these problems by hand. I mean, I can give you the explanations, but you have to actually sit down and compute each one of these inertia matrices using either the formulae or the statements that are given here, right? So this is telling you moment of inertia in the y direction. You can see y is out of the plane of the pipe, is 1/12 ml squared, and you're computing it about the mass center of the pipe G. Then if you wanted the mass center's moment of inertia, you would jump to another point, and that's what we have to do. So essentially, again, focusing just on the pipe A, I of A about O. The inertia matrix of this pipe A about the point O is going to be equal to the inertia matrix of the pipe A about its mass center plus the inertia matrix of the mass center about O. And you'll see that I've actually done that at the very bottom over here when I try to look at the inertia matrix of A about O. I say it's going to be equal to the mass, the inertia matrix of the rod about its mass center, and then of the mass center about the point O. So I have to know how to compute this, and I have to know how to compute this. The first of these matrices I calculate right at the top. I say it's given by this thing here. How do I know this? Well, this is essentially coming from the fact that this is the inertia matrix of the pipe about its mass center. So we just spoke about that. So that's just by looking at this table and knowing like what x, y, and z are. And that's kind of indicated in the figure, right? X is pointing out, y is pointing up, and z is pointing that way. So for each of these bodies, that x, y, and z is going to be the same, but you're going to have to move it to the right point. So x and y are going to have 1/12 ml squared, or mb squared in this case, and the z direction is going to be 0. So you can see that the very bottom, the diagonal element is 0, whereas the others are 1/12 ml squared, and m is some function. You have to like make the substitutions, but you can see it's m over 4 and things like that. I'm not going to go over that. You have to learn these simplifications and substitutions, of course, but you can see why you get mb squared over 48. And then I compute the mass center, the inertia matrix about the point O. And for that, that's actually even more trivial because it doesn't require a table, but it just requires you to like revisit definitions of how we compute mass centers and inertia matrices using the concepts of mass centers, right? So look at this formula and try. I mean, you have to make the substitutions for what is the P vector that locates the mass center. So you have to be able to make that substitution in the appropriate frames, take the cross products and then the dot product, and you'll get the results that I've gotten here. Now, the reason I'm not going over how each element is computed is because it is a fairly trivial computation. In fact, I'm giving you the formula here. It's doing the computation, but you need to be able to know how to like actually get those position vectors right. That's just a very simple vector, position vector writing task, which to some extent I've also shown you how this works for another question that was asked on QM Plus. So I'm hoping that essentially this is showing you how we're getting to whatever we're getting. I'm actually manually computing each of these. I know that I did this by hand and I put this in the matrix form and I saved it under the variable I underscore matrix of A star about O. And then I add this to this and I get what is I of matrix of A about O. This is the rod's inertia matrix about O. I repeat the same process for B about O. Again, it's just the parallel axis theorem again we use on B. We use the same thing for C, but you have to actually be able to take these cross products and dot products and write the position vectors in the way that you need to for the mass center about that point O. And this stuff just comes from looking at the fact that it's a pipe. All right, I'm hoping that this is enough, and if it isn't, you have to actually sit down and solve the problem. It will be something that I think you would actually take a lot out of. So I cannot encourage you to sit with a pen and paper or with the computer and like put in the right formula and see how I got these as the numbers.